In the name of God, I am Muhammad Taki, a master's student currently studying at the University of Mazandaran. In this section, we will introduce geopolymer concrete. Today, concrete is recognized as the most widely used construction material in the world, a substance that forms the backbone of modern cities, bridges, tunnels, and critical infrastructure. However, within such a vast field, there lie significant environmental and performance-related challenges. The production of Portland cement, the primary component of conventional concrete, is responsible for approximately 8% of global carbon dioxide emissions. This concerning fact has motivated researchers to seek alternative materials that can offer both adequate performance and greater sustainability. Among these, geopolymer concrete has emerged as a promising and innovative option. It is a material derived from the alkaline activation of pozzolanic substances, such as fly ash or blast furnace slag, which, without relying on Portland cement, can achieve remarkable mechanical and thermal properties. Yet, a crucial question arises. Can geopolymer concrete outperform conventional concrete under severe conditions, particularly at elevated temperatures? In this study, we investigate, through scientific and laboratory-based experiments, the behavior of geopolymer concrete when subjected to thermal loading. As a first step, we introduce geopolymer concrete. This material is produced using fly ash, blast furnace slag, GGBFS, or metakaolin, combined with an alkaline solution, typically consisting of sodium hydroxide and sodium silicate. The mix design is based on the ACI 211 standard for concrete. However, since no standard mix design exists for geopolymer concrete, we relied on published research studies as references. The adopted mix proportions are presented in the following table. To begin, we entered the concrete laboratory and started by oiling 10 centimeters rubber molds. Next, following the mix design, we prepared the fly ash, slag, coarse aggregates, and fine aggregates and began the mixing process. For the preparation of geopolymer concrete specimens, the sand and gravel were first mixed in a mixer for 60 seconds. Then, the activating powders, including slag and fly ash, were gradually added to the mixture, and mixing continued for another 60 seconds. At this point, it is important to note that the sodium hydroxide solution was pre-mixed with sodium silicate. Finally, this alkaline solution was slowly added to the sand, gravel, and powders in the mixer. For the curing of geopolymer specimens, after casting, the samples were kept in their molds for 24 hours under plastic covering to prevent moisture evaporation. After this period, they were placed in an oven at 60 degrees Celsius for 24 hours. Subsequently, they were removed from the oven and stored under ambient laboratory conditions. For conventional concrete, after casting into plastic molds, the samples remained in the molds for 24 hours. They were then demolded and placed under wet burlap. To prevent moisture loss, the specimens were also covered with plastic sheets. The burlap was regularly moistened at specified intervals to ensure that the specimens were properly cured for 28 days. This experiment was conducted in accordance with ISO 834. In the thermal exposure phase, the specimens, previously conditioned under laboratory conditions, were placed in a furnace at 60 degrees Celsius the day before testing. To ensure uniform heating, the specimens were arranged on refractory bricks so that all four sides were equally exposed to heat. After completing the cyclic thermal treatment, mechanical and physical tests were performed, including compressive strength, electrical resistivity, weight loss, water absorption, and porosity. The temperature curve was plotted according to ISO 834. Due to the furnace capacity, reaching the target temperature required additional time, resulting in minor deviations from the standard heating rate. Once the target temperature was achieved, the furnace was maintained at this level for 2, 4, or 6 hours. The specimens were then allowed to cool naturally inside the furnace. At the end of the thermal cycles, the specimens were subjected to compressive strength testing. This test was carried out using a hydraulic press with a 200-ton capacity at a loading rate of 0.25 megapascal per second. Compressive strength measurements were conducted 10 days after the final thermal cycle to fully evaluate the influence of elevated temperature exposure. Electrical resistivity test. The electrical resistivity test is one of the common methods used for quality control of construction materials. Due to its rapid execution and non-destructive nature, it has found wide application. The procedure involves three main stages: specimen preparation, electrode installation, and application of electrical current. 1. Specimen preparation. First, the specimens are immersed in water for 24 hours to ensure full saturation. Then, their external surfaces are dried with a lint-free cloth to achieve a surface saturated dry (SSD) condition. 2. Electrode installation. Special electrodes, typically made of copper or steel, are placed on opposite sides of the specimen to allow the passage of electrical current. 3. Application of electrical current. After installing the electrodes, a specific voltage, usually between 10 and 60 V, is applied to the specimen. For this step, the resistivity testing device is switched on and the frequency is initially set to 50 Hz. Then, by pressing the control key, the voltage is gradually increased until it reaches the target value, around 60 V. It should be noted that, due to voltage drops along the testing circuit, the applied voltage is generally set slightly above 60 V to ensure that the actual voltage across the specimen reaches the desired level. Water absorption and porosity test. The water absorption and porosity test is one of the standard methods used to evaluate the durability and permeability of concrete. This test measures the ability of concrete to absorb water as well as the amount of voids and porosity present in its structure, characteristics that have a direct influence on the mechanical strength and long-term stability of concrete under environmental conditions. Test procedure. First, the dry weight of the specimens was measured. The specimens were then immersed in water for 24 hours to achieve full saturation. After this period, they were removed from the water and their external surfaces were dried with a cloth. Subsequently, their saturated weights were recorded. Compressive strength evaluation. The following diagram illustrates the variation in compressive strength of three types of concrete in megapascal, RC, G1, and G2, at temperatures of 20, 300, and 600 degrees Celsius. The results indicate that compressive strength decreased in all specimens with increasing temperature and holding time. However, the RC specimens experienced less reduction compared with G1 and G2. This superior performance is likely attributed to the formation of combined CSH and NaSH gels, which produce a denser and more heat-resistant structure. In contrast, specimens containing only one type of pozzolan exhibited simpler and more porous microstructures, leading to greater strength loss. The following table presents the percentage reduction in compressive strength for the three concrete types after a single thermal cycle at holding times of 2, 4, and 6 hours. As shown, the greatest reduction occurred in G1, followed by RC, and finally G2. With increasing temperature up to 600 degrees Celsius, these reductions became more pronounced. In evaluating the effect of temperature and holding time on compressive strength over 3 thermal cycles, RC concrete demonstrated the most stable performance. This was attributed to its denser microstructure and stable CSH gel network. In contrast, G1 and G2 concretes, due to differences in gel composition, showed greater strength loss, particularly G1, which lacked fly ash, Fa. The inclusion of Fa in G2 improved its thermal performance and reduced its vulnerability. Additionally, at 300 degrees Celsius, the increase in holding time had the most significant effect on reducing the strength of RC concrete, while at higher temperatures, G2 performed better. The subsequent table shows the compressive strength reduction of the 3 concrete types after 3 thermal cycles. Comparison with the previous table reveals that increasing the number of cycles from 3 to 6 led to greater strength reduction in all concretes. At 300 degrees Celsius, G2 performed better than G1 and RC. However, at 600 degrees Celsius and longer holding times, G2 experienced the greatest strength loss. Findings from other studies have also confirmed the adverse effect of prolonged exposure at elevated temperatures on the strength of geopolymer concretes. Electrical resistivity evaluation. The following diagram illustrates the range of electrical resistivity variations for 3 types of concrete: RC, G1, and G2, at temperatures of 20, 300, and 600 degrees Celsius. The unit of measurement for resistivity is ohm meter. The results show that the changes in electrical resistivity from 300 to 600 degrees Celsius compared to ambient temperature were smaller in G2 than in G1 and smaller in G1 than in RC. This indicates that concrete containing a combination of GGBFS and FA exhibits greater stability at elevated temperatures compared with concrete made solely with GGBFS. In contrast, concrete containing 100% GGBFS tends to form crystalline phases and undergo microstructural changes at high temperatures, leading to localized porosity and facilitating ionic transport pathways. As a result, its electrical resistivity decreases while conductivity increases. The table presenting the percentage reduction in electrical resistivity after one thermal cycle shows the results for RC, G1, and G2 at holding times of 2, 4, and 6 hours. As can be observed, RC experienced the greatest reduction in resistivity. With increasing holding time from 2 to 4 and then 6 hours, the percentage reduction decreased in all three concrete types. Furthermore, while increasing the temperature from 300 to 600 degrees Celsius resulted in greater resistivity loss in RC, G1 and G2 showed lower reductions at 600 degrees Celsius compared to 300 degrees Celsius. On the other hand, G2 exhibited greater resistivity loss with longer holding times. In examining the effect of the number of thermal cycles, it was found that increasing the cycles from 1 to 3 produced different behaviors among the concretes. At 300 degrees Celsius, G1 showed the highest increase in resistivity reduction, whereas RC exhibited minimal changes and G2 remained relatively stable. At 600 degrees Celsius, RC and G1 experienced lower reductions in the third cycle compared to the first, while G2 displayed greater reductions across all holding times. Overall, increasing the number of cycles led to decreased resistivity loss in RC, relative improvement in G1, and further deterioration in G2. The table corresponding to 3 thermal cycles shows the percentage reduction in electrical resistivity over different holding times. Increasing the number of cycles from 3 to 6 resulted in higher resistivity loss for RC, indicating reduced stability under repeated thermal exposure. In contrast, the geopolymer concretes G1 and G2 exhibited smaller reductions in the 6th cycle compared to the 3rd, reflecting greater structural stability against repeated heating. This behavior is attributed to the beneficial role of fly ash, Fa, with its high silica and alumina content, which promotes the formation of stable amorphous gels, such as NaSH, at elevated temperatures. These gels not only strengthen the matrix, but also help prevent crack propagation. These findings are consistent with previous studies, including those of Bayfarnia and Biotti, which demonstrated that geopolymer concretes containing slag exhibit greater mechanical stability at high temperatures compared with Portland cement concretes. Water absorption. This diagram illustrates the range of water absorption variations for 3 types of concrete: RC, G1, and G2, at temperatures of 20, 300, and 600 degrees Celsius, with holding times of 2, 4, and 6 hours during the first thermal cycle. At elevated temperatures, all specimens exhibited higher water absorption compared to ambient conditions. RC showed the greatest increase, likely due to the formation of microcracks, evaporation of bound water, and microstructural degradation under thermal exposure. In contrast, G1 exhibited the lowest water absorption under all conditions, indicating its dense structure and high thermal stability. G2 displayed intermediate behavior, with water absorption lower than RC but higher than G1. The corresponding table shows the percentage increase in water absorption during the first cycle for the 3 types of concrete. The highest absorption was recorded for RC and the lowest for G2, while G1 showed intermediate performance. As the temperature increased from 300 to 600 degrees Celsius, all values rose further, with RC consistently exhibiting the highest absorption. Increasing the number of thermal cycles from 1 to 3 induced repeated expansion and contraction within the concrete structure. These alternating thermal stresses gradually produced microcracks and increased both surface and internal porosity, thereby raising permeability and water absorption. Thus, even at constant temperatures, repeated thermal cycling can reduce concrete durability by creating additional pathways for water ingress and weakening the structure. The table corresponding to 3 cycles shows that water absorption increased in most specimens. With further cycling from 3 to 6 cycles, all specimens exhibited additional increases in water absorption. Among them, G1 consistently showed the lowest values. Even at 600 degrees Celsius and after 6 cycles, its absorption remained controlled. G2 maintained intermediate performance, which can be attributed to the presence of 40% fly ash, Fa, producing a relatively more porous structure. These findings align with the studies of Richard et al. And Nematolohi et al., who also reported that geopolymer concretes exhibit lower water absorption and greater resistance to thermal cycling compared with Portland cement concretes, particularly in the presence of high GeBFS content, which promotes the formation of dense CSH gels. The table below presents the percentage increase in water absorption after 6 cycles for the 3 types of concrete. Porosity. This diagram shows the range of porosity variations during the first cycle for the 3 types of concrete at 20, 300, and 600 degrees Celsius. Overall, porosity values varied significantly with the type of concrete, from RC to G1 to G2. Results indicated that at ambient temperature, the porosity of G1 and G2 was 26.5% and 113.7% higher, respectively, compared to RC. However, at 600 degrees Celsius, these differences decreased to 11.2% and 1.4%, respectively. This trend can be explained by cement paste degradation, evaporation of bound water, and the development of thermal microcracks in RC, versus the formation of a denser glassy phase within the geopolymer matrix. The presence of CSH gels and the inherent high thermal stability of GeBFS and Fa are considered the main factors contributing to the superior performance of geopolymer concretes. The table corresponding to the first cycle shows that the highest porosity reduction occurred in G2, while the lowest was recorded in RC, with G1 showing intermediate performance. With the temperature raised to 600 degrees Celsius, porosity reduction decreased in all specimens. When the number of thermal cycles was increased from 1 to 3, porosity reduction showed a clear dependency on temperature. At 300 degrees Celsius, porosity reduction decreased, reflecting the gradual weakening of the concrete structure and the propagation of microcracks, leading to relative stabilization of porosity and reduced capacity for further decline. In contrast, at 600 degrees Celsius, porosity reduction increased, likely due to more severe structural degradation, greater release of bound water, and reopening of previously sealed pores, all of which contributed to greater porosity loss compared to the first cycle. With additional cycling from 3 to 6 cycles, porosity reduction at both 300 and 600 degrees Celsius decreased slightly. However, the reduction was relatively small and in some cases marginal, with differences between the 3rd and 6th cycles amounting to only a few percentage points. This limited change can be attributed to the attainment of a microstructural stabilization stage, where most evaporation, cracking, and water release had already occurred in the early cycles, leaving subsequent cycles to produce only minor alterations in pore structure. The table presents the porosity reduction percentages after 6 cycles for the 3 types of concrete. Section 5. Conclusions and Recommendations. 1. The rate of compressive strength reduction due to heating from 20 degrees Celsius to 600 degrees Celsius was calculated as 0.035 in megapascal per degree C for RC concrete, 0.032 for G1, and 0.018 for G2. When the concrete type was changed from RC to G1 and G2, the average compressive strength at ambient temperature, 300 degrees Celsius and 600 degrees Celsius, decreased by 47.7% and 61.1%, 68% and 57.3%, and 79.2% and 72.4%, respectively. 2. According to the results, at ambient temperature, the loss of compressive strength in G1 concrete was lower than that of G2 compared with RC. However, at elevated temperatures, the reduction in compressive strength relative to RC was smaller in G2 compared with G1. 3. G1 concrete demonstrated relatively stable behavior at elevated temperatures. Although its initial electrical resistivity at ambient temperature was lower than that of RC, its decline at 600 degrees Celsius was more gradual, indicating favorable thermal performance. G2 concrete exhibited intermediate behavior between RC and G1. Although its initial strength was lower than that of G1, the reduction in strength remained relatively controlled with an increasing number of thermal cycles. 4. With rising temperature and the number of thermal cycles, water absorption in RC concrete increased significantly. In contrast, G1 consistently exhibited the lowest water absorption under all conditions, remaining relatively stable even after 6 thermal cycles at 600 degrees Celsius. G2 again showed intermediate behavior, with water absorption lower than RC but higher than G1. 5. By changing the concrete type from RC to G1 and G2, the average porosity at ambient, 300 degrees Celsius and 600 degrees Celsius increased by 26.5% and 25.7%, decreased by 11.8% and increased by 14.4%, and increased by 9% and 10.1%, respectively. At ambient temperature, porosity in G1 and G2 was 26.5% and 113.7% higher than RC, respectively. When the temperature increased to 600 degrees Celsius, these values compared with RC at the same temperature were 11.2% and 1.4%, respectively.